Hello, just saying hello and welcome back to the conference. Today is day 4, AI Day, the fourth of what have been 3 really wonderful days so far. Extremely high quality talks, very interesting. I feel like more than any conference that we've had in the past, people are really connecting to the theme, mathematics and neuroscience and AI, and thinking about how to connect across these different adjacent disciplines, share ideas, and challenging data. We've been really excited about today, AI Day, in particular, because we've got 2 exceptional keynotes really representing pioneers of the field, also people that have engaged widely with these neighboring disciplines. And we're also really excited because it's sort of the culmination of the conference in general, and we've had such amazing, energetic participation from all of yourselves and the speakers, and we really have been just so fortunate to have such a great dialogue going on. So for AI Day, we will have our first speaker who's just flown in from Stanford, a sort of 30-hour flight yesterday, Professor Jay McClelland. So Jay is the Lucy Stone Professor of Psychology at Stanford, where he's been for quite some time and helped set up these really amazing initiatives, one being a core member of the Parallel Distributed Processing Group, writing a book with David Rumelhart that sort of brought shepherds down from the hills in order to study neuroscience and begin thinking about computational paradigms for intelligence. Also being a member of the Stanford HAI group, which at the moment is a sort of very influential and interesting force in AI. I highly recommend following them on socials to keep up to date with all of their work. And more than that, I think Jay has been just an amazing thinker and mentor to all of us in the field to help us keep thinking about thinking in sort of challenging ways and keep pushing boundaries. So Jay, thank you ever so much for flying across and giving the opening talk. We're all really excited to hear what you have to say. Let's welcome Jay to the stage.
Okay, thank you very much. I see my title on my screen. Is that something I need to do there? Yeah. So, are people still smarter than machines? The first sentence of the PDP books was, why are people smarter than machines? And we said at that time that it's because we're far more capable of exploiting many simultaneous constraints, of using information sort of mutually between different modalities to simultaneously settle on interpretations of the world and to choose optimal actions. And when we thought about the AI systems of the time, they were really quite brittle and, completely just explicit rules that would break at the slightest provocation. Or at least that's how we felt about it. And so we argued that the AI systems of the day would never work, and we proposed a set of ideas called parallel distributed processing as an alternative. So what were those ideas? Well, they were the ideas that processing in our minds occurs via the propagation of graded activation signals among simple processing units, that representations are distributed patterns of activation across these units, that knowledge in the system is in the connection weights among the units, and that learning occurs through adjusting these connections to match a target output or maximize reward or maximize some other objective. And, at the time, these ideas generated a huge amount of enthusiasm and interest, but they had some limitations. And toward the end of the last century, a lot of people were saying, we need something else. We need, Bayesian ideas. We need explicit symbolic models that, yes, they use probabilities. They can deal with graded constraints, but they're otherwise very explicit symbolic models of the kind that we were, in some sense, thinking would probably never work. So actually, there was a sort of a second neural network winter, or maybe a third one, depending on how you count. But about 10 years after that, of course, things really began to change. And in some ways, today's AI systems are pretty smart. So they function well enough to be used every day for speech recognition, language translation, and many other things. They exceed human performance in games like Go and chess, and they're getting more and more powerful every day. Large language models and multimodal models, visual language models, become ubiquitous tools threatening to replace humans in many domains. And this is what Sam Altman had to say when GPT-3 came out. And, basically, hey, we've got it all solved here is what he said at that day on November 30th in 2022, right when they've released the first chat GPT. Is he right about that? Are we really there? Are we almost finished solving intelligence? Well, there was a major innovation that really did advance the field. It was completely unanticipated before it occurred. I mean, a couple of people were thinking, oh, gee, there's these limitations to the models we have right now. We need something better. They're not really perfect. But all the papers were saying, oh, we're doing better every month. We're beating the benchmarks every time. But then this idea came along, and pretty soon, attention was all you needed. So that was a big change. And I think my main message today is that there are going to be a few more of these in the future. We don't know what the future will hold, but there are reasons why this beautiful idea, as smart as it is, as useful as it is currently not fully doing all the work that ultimately I would like to see our intelligence systems do. And hopefully we'll talk about that kind of idea today, and I'll say a bit more about some of the things I think are not being captured. So what is this beautiful idea? Imagine that you are somebody interpreting a sentence, and the sentence is, upon hearing the doorbell, Amy's Labrador began to bark. Now, when the word bark comes in, it in and of itself is an ambiguous word. It could refer to the outer covering of a tree, or it could refer to the sound made by a dog. And so the question is, well, how do you figure out what that word actually means, and how do you use that information to help you figure out what might come after it? So the idea in attention is what I call query-based attention, is that the word bark issues a query to the context, and the query is a pattern of activation over a set of neuron-like processing units, which we've illustrated here by those little up and down little gray bars, which indicate degrees of activations of units in a vector. And they get compared to keys, vectors that represent items in the context. And there's a pretty good match between this query from bark and a key associated with the word Labrador. And maybe a partial match with the key associated with the doorbell. So we get a goodness of match score. Then we put it through a softmax function to get a vector of weights that adds up to 1, so that we then return a return vector weighted across all the items in the context by this goodness of match score to say, well, this is what I'm saying back to you in answer to your query. And it's some sort of composite pattern that comes from all the items in the context weighted by their attention scores. Very well. So this not only could tell us, oh, it's probably the sound of a dog and not the bark of a tree, but it also probably gives us nuances, because the Labrador probably barks loudly, and we know that. So if this was a sentence that we actually put into GPT-3, and my colleague Rav Suri did that, the completion that it would produce afterward would be actually loudly. So that's how it works. That's how attention allows context to influence language models' behavior. And I want to just call attention to the fact that it's incredibly powerful because at each word, let's say that the word to the farthest right here is the word bark coming in. At each word, we can query everything in the preceding context. I've shown only 2 previous words, but this could go on for 10,000, 100,000, 10 million tokens of context. We could query all of this stuff to get information back from a very huge context window. And that was something that the earlier models did not allow. They had a narrow bottleneck that information from context had to be sort of pumped down into, and there just wasn't enough capacity to access all of the relevant contextual information that would be useful in any given situation. It was what we were dreaming about. Rumelhart really wanted context to be exploitable in all of its glory, and this was great. So, we have this other example is similar, but it just like we could get a chance to think about the scale of these things. So these models, GPT-3 large was 96 layers deep of these transformer modules with 96 attention heads within each layer. And the context window was like 4,000 for training, but could be larger for a test time. And it was a really incredible advance in our ability to exploit context and do things like that. And they're good at using context. So Rav asked ChatGPT this question. I use its bark to make paper. In the previous sentence, make your best guess about what it refers to. ChatGPT says, in the given sentence, the word it most likely refers to the bark of a tree. Second prompt, I use its bark to keep the house safe. What does the word it refer to? In the given sentence, the word it likely refers to a dog, etc. It's protective behavior. It suggests a protective behavior associated with dogs, blah, blah, blah. Okay, so this is great. I love it. These are amazing models from this point of view. But large language models are supposed to be good at reasoning and problem solving too. And what I want to ask today is, how smart are they really? So here's an example from around the same, a year and a half ago now, I think, I asked this question. I'm asking ChatGPT, can you place one X in each row and column of a 4x4 grid without any of the X's being adjacent, either horizontally, vertically, or diagonally? Now, maybe off the top of your head, you don't know the answer to that question. But GPT-4 thinks it does. It says, yes, it's possible to place one X in each row and column of a 4x4 grid without any of the X's being adjacent, horizontally, vertically, or diagonally. Here is one possible solution. Can you see it? Do you think it got it right? You can't see it. You can see it. Yeah. Okay, so there are X's diagonally adjacent in the second and third row. Okay, not very good answer. And then it said, in this arrangement, none of the X's are adjacent in any direction, meeting the specified conditions. Very nicely formed answer. I said, your grid seems to have diagonally adjacent X's in the second and third rows. Do you agree? Apologies, my mistake. You are correct. My previous example does have diagonally adjacent X's in the second and third rows. Unfortunately, it's not possible to place X's in a 4x4 grid without any of them being adjacent, horizontally, vertically, or diagonally. Now, I already knew the answer to this question, and so I am showing it to you here. And if you don't allow wrapping, right, there are no x's adjacent in any of the specified ways. So the model, did something that sounded intelligent, but it really wasn't particularly smart. So now I'm going to ask a question, and I take this question very seriously because I don't think that we are, in any sense, ideal, perfect intelligence either. So I'm going to ask us to think about the question, are we any smarter? Here's a case where people seem to have very strong intuitions. Let's see what you all think. Here's a question for a game contestant. A Cadillac is hidden behind one of 3 doors. Goats are hidden behind the other 2. A contestant initially selects door 1, and if he's right, he'll win the Cadillac. If the Cadillac is behind that door, he'll win it. The game show host then reveals that there's a goat behind door 3 and offers the contestant a chance to change his guess. Should the contestant keep his original guess or switch to door 2? What? Depends on if you like goats? Okay, well, so I set you up to be skeptical, I hope, right? So you're like, oh, I'm not going to say. Okay, but the correct answer is you will increase your chance of winning from 1/3 to 2/3 if you switch. Most naive human participants, however, choose to stay rather than switch. And according to Wikipedia, when this puzzle and this answer were published in a Parade magazine column in 1990, approximately 10,000 readers, including nearly 1,000 PhDs, wrote to the magazine, most of them calling her wrong. Even when given explanations, simulations, and formal mathematical proofs, many did not accept that switching is the best strategy. And according to a mathematical columnist named Andrew Vasonyi, when he mentioned this problem to his friend, the famous mathematician Paul Erdős said, no, it's impossible. It should make no difference. So a brilliant mathematician can be very wrong and convinced of their answer. And it happens to everyone. Humans are extremely susceptible to self-congratulatory beliefs about their understandings of all kinds of things. I think that's one of the biggest problems we face in the world today. But back to people and machines together, here's another example which is going to make a slightly more specific point. And it was very central to the debates that we were having in the 80s about what was the fundamental nature of our human cognitive ability. So this is a simple logic game. And it's, okay, let me just present it to you. These are 4 cards that you might see if you were a participant in this experiment run by Peter Wason back in the 50s. Each card has a number on one side and a letter on the back. So some of the cards are face down, some of them are face up here. Which card or cards must be turned over to check if the cards all obey this rule? If a card has an even number on one side, then it has an X on the other side. Okay, so that's the question. And most people, almost everyone, turns over the 6, which is good. But very few people turn over the Z, which is the crucial card, or the one that people don't remember to turn over, because if it did have an even number on the other side, then it would be violating the rule. Okay, it's a very simple logic problem. Hardly anyone gets it right, including trained logicians, when they're given it as a puzzle without mentioning logic to them or anything like that, And Wason was profoundly interested in this outcome. But it was, it's very easy to replicate. However, a very important further fact is known about this kind of game, and that is that if you put it in a common sense situation, people do much better. So here's an example. Each check to the right is for a purchase at a store. Each check has an amount of a purchase on one side and a box for the manager's approval on the other side. Which check or checks must be turned over to see if they obey this rule? If a check is for more than $25, then the manager's approval box must be checked on the back. So now, people are much more likely to turn over the check that hasn't been approved by the manager, because they're like, well, why? Why? Some people have claimed that evolution prepared us for this. Others of us think that we learn in various contexts about expectations and what would happen if various things were violated, and we have intuitive stories in our mind that help us flesh out scenarios that are familiar to us, and we might say, oh, gee, the cashier who accepted that check is going to get fired, if that doesn't turn out. And so our thinking is heavily infused by our knowledge and common sense reasoning ability. And this is true of humans and large language models. So this is data from 2 groups of human subjects and 5 different language models. And you can see that all groups except for the group on the far left showed basically an advantage for realistic compared to completely arbitrary examples. There was a nonsense condition. The models varied a little bit about that, but in almost all cases, the green, which is the realistic, is above the arbitrary, which is pink, and basically performance is very poor in the arbitrary condition. Which group was the worst group? Well, it was the fast-responding humans in the experiment. If you run humans on MTurk and you don't really ask them to pause and think, they really perform extremely poorly in general. And thinking is actually hard, But humans and language models, and that's the key point here, show these content effects, right? This paper that this was in showed this in different domains beyond just this one example. But the point is, I think, very important, and it's related to what we were looking for when we wanted to have language models or when we wanted to use neural networks to understand our own cognition, which was that our cognition seems to be richly infused by our past experience and our ability to use what we know to guide our thinking. So here's an interim summary. Machines can hallucinate, but humans can too. Humans and machines can fail seemingly simple logic puzzles, but can seem smarter if these problems are posed with familiar scenarios. This invites the conclusion that we're not intrinsically the kinds of logic machines some once claimed that we are, and that our machines aren't intrinsically logic machines either. There's a kind of natural intelligence here in both ourselves and our machines, much like what we sought to capture in the PDP work in the 1980s. But hey, humans can go beyond their natural intelligence. We have, Richard Feynman, we have Charles Darwin, we have Isaac Newton, Einstein, Rumelhart developing backpropagation, Demis Hassabis driving forward to make AI so powerful. Humans are not limited by their natural intelligence. And that's very important, I think. That's a very fundamental theme, I feel, about ourselves, that, over the course of history, we have organized ourselves culturally, and we've developed systems that allow us to leverage our own abilities so as to make our ability to think far, far more powerful than it would otherwise have been. And we've invented these amazing machines now that are helping to do that very same thing. So that's all amazingly great, but how smart are the machines as we have them today? And if they're not as smart as we can be at our best, then we've still got lots of interesting challenges ahead. So I'm going to make points about how we're smarter than machines, and there's two important ways in which I think we're smarter than machines. They are related to each other. So first of all, today's large language models are trained with up to 100,000 times more training data than a human could experience in a lifetime. So just to make sure you appreciate this, I've got a graphical representation of 100,000 to 1 on this screen. Down there in the lower left-hand corner, there's one pixel representing one tiny little square representing the amount of data that a human could be exposed to in a lifetime. And the big blue area is the amount of data that DeepSeek v3 base was trained on when, as described in their paper from a few months ago. Okay, it's like a lot more data, 100,000 times more data to get these machines to be as smart as they are. Now, you could quibble that there's all kinds of reasons for this, but I'm thinking that we're more efficient in a very important way than these machines are. And that's the fundamental question, one of the fundamental questions I think we need to answer. So here's the second point, and it's very closely related. These machines can fail to generalize in seemingly obvious ways, while people sometimes generalize far more successfully. So here's the example of this that caught my attention about a year ago when it came out, a paper called The Reversal Curse, in which Berglund and collaborators observed that a language model might know the answer to the question, who is Tom Cruise's mother? They would answer, Tom Cruise's mother is Mary Lee Pfeiffer, but if asked, who is Mary Lee Pfeiffer's son, the same model would say, as of September 2021, there is no widely known information about a person named Mary Lee Pfeiffer having a notable son. So this is called the reversal curse because saying something like A is B, Mary Lee Pfeiffer is Tom Cruise's mother, and saying Tom Cruise's mother is Mary Lee Pfeiffer are not the same thing to these models, even though they seemingly are exactly the same thing to say to us. And indeed, they showed that if you fine-tune these models, they really only learn it in one direction. So you give it synthetic facts that you made up, like Daphne Barrington is the director of A Journey Through Time, and you ask them, who is the director of A Journey Through Time? They have no idea. There's actually no indication at all that having trained it on the forward direction helps the model with the reverse direction. Now, this may not be too surprising, right? If you think about this transformer that I showed you a version of before, and you think about what's going on when the model learns this stuff in its connection weights, you could begin to see why this would be true, right? So I've got a generic example here, like John's father is Bill. If you've trained the model to go from John's father is to predicting Bill by training connection weights here, well, what would it know how to do if you asked, Mary Lee Pfeiffer's son is, or the reverse, Bill's son is? It wouldn't know anything about that, right? The different words. So this is not actually the learning system that we could possibly be using when we encounter new facts like this, right? And we're doing something else beyond this kind of burning stuff into our connection weights in this way. But more generally, the models, in order to learn anything like Tom Cruise's mother is Mary Lee Pfeiffer in a usable way, they've got to experience in all different orders with all different answers in order to cover the space properly so that they'll be able to. And that's why, I'm sure that's a couple of orders of magnitude worth of the problem. We need an architecture that isn't that dumb. So I thought I had 40 minutes. I only have 30 minutes, so I won't be able to go into this example in gory detail. But this is some work that my PhD student Andrew Nam did while he was with me. It showed that humans can learn far faster and generalize better than connection-based learning models do, kind of illustrating this point in the domain of the game of Sudoku. I'm going to have to summarize it a bit for the sake of time, but the basic idea is that we showed people grids like this, and we walked them through solving for the digit that has to go in the green square, okay? So each participant got a grid like this, and they got walked through how to solve it. Each participant's grid was a little different in that the particular column that the highlighted square was in could vary. It could be a row instead of a column, and the particular cell could vary from individual to individual. But there were always these two digits that weren't actually in the highlighted column, and one of the two always had to go in the highlighted cell, okay? And we screened for people who had no prior Sudoku ability. We gave them a very simple little Sudoku. If they solved it, they weren't allowed to be in the experiment. And we found that a third of the people who we walked through this tutorial, but only a third, successfully figured out how to solve these puzzles. They didn't necessarily get it on the tutorial, but over the course of 25 practice examples, with the same arrangement of everything in the grid, they got it. And so these are the solvers. This is the results from the solvers. On the first trial after the tutorial, about half of them got it wrong, but they gradually eliminated their errors, and they, at the end, they were making occasional errors. And when we tested these same people with all possible variants of the puzzle, changing the row, the column, which cell it was, which digits could be used, they were hardly affected by that at all, okay? They had learned a completely generalizable solution strategy from a very limited range of examples. And if you teach a neural network this, it overfits to the exact specifications of the training example and doesn't generalize at all. So that's the quick summary of that. I'm flashing through the results. You switch which digits were important. People are completely unfazed by that. They do show a slight decrement in accuracy if you suddenly switch them from rows to columns, but they recover very quickly after a small number of examples. Okay, so I want to highlight something that I think is very important about what people are doing in this context, and that is that they are coming up with an explicit understanding of what they're doing that allows them to solve this problem. And this is not completely accidental. The tutorial was an explanatory tutorial. We explained the steps of this and why it worked. But not only did we explain it to them, but they could explain it back to us if they were solvers. Not all of them did a perfect job of explaining it back to us. And some people would say, well, see, some of them just know it intuitively. Maybe they were lazy, I'm not entirely sure, but here's an example of a solver. And I'm using this example here with 2s and 9s so you can follow it. We asked them to explain how they solved a particular problem we'd given them at the end of the experiment so that somebody else could execute the same solution strategy. And so this person said, I located the larger square with two numbers in it, the 2 and the 9, the one down in the middle of the bottom row. This told me the green square would have a 2 or a 9. I then checked to see if 2 could fit in one of the 2 remaining blue squares. Since there was already a 2 in each row, I knew 2 had to be the solution to the green square. That is completely valid description of what you have to do to get this right. A non-solver said, I went through a process of elimination by checking which numbers were already included in each square, since you can't duplicate numbers. But to be honest, I'm not sure if the 2 should go in the first, third, or fourth blue box, or if the 9 is in the second, third, or fourth. Sadly, these puzzles have made me feel not very bright. So the people who can solve these things explicitly understand what they're doing in a way that they can express usually. I shouldn't say always, but usually. So the idea that we learn by having things explained to us and gaining an explicit understanding is crucial to our ability to be intellectuals and contributors to the process of science. And it's what they teach us in school. And it's the product of, the evolution of ways of thinking that have come down to us from the philosophers of the past and from the people who've invented thinking systems that we rely on every day. And I believe that our ability to think systematically and clearly is heavily influenced by these exposures and traditions. And it's not convincing evidence, but in this particular study, nobody who hadn't had high school algebra or geometry was a solver. So some experience with explicit reasoning with rules that manipulate symbols. It's a paradox. We learn to be symbol processors, okay? We're not innately symbol processors. That's my point. All right. So here's something very interesting. Unlike models that are fine-tuned, models do not exhibit the reversal curse when the given information is available in their context window. So if I tell you that John's father is Bill, then you can answer the question, Bill's son is John. Even a fairly simple model can do this. Okay, so here's this thing laid out in my little schematic of the language model. John's father is Bill, period. And then the next tokens are Bill's son is John. And it's actually more likely to complete Bill's son is John if the first sentence is John's father is Bill than if the first sentence is Bill's son is John, because it doesn't think that you should just repeat yourself. I mean, that's how we understand that fact. So the model has learned this. But there's something very frustrating to me about the way that it's learned it. We can't find it anywhere in there. It's distributed throughout the attention heads and various vectors of these models in ways that is very difficult to pin down. And my current conjecture is that it's actually figured out how to do this in all possible different orders and permutations, rather than figuring out what I think is more natural, which is that we sort of have a sense of, oh yes, there's a father-son relation here, and we can probe it in many different ways. Okay, so I'm supposed to finish up pretty soon, but I did have one more experiment that I wanted to share with you. And we can ask, well, okay, so is in-context learning the solution? And I think I've already hinted that I'm not totally sure it is the entire solution, but I want to illustrate something specific about one way in which it's not the solution. And so this is an experiment that my student, Jerome, completed this past year and has been accepted for presentation at the Cognitive Science meeting this coming July. So what you're going to see is that, the models can take in information and hold several propositions in context and even do a reasonable job reasoning with it, but they don't do something that humans do with the information that they've learned. And that is to organize it proactively, to structure the way they understand something so as to be able to use it efficiently. So this is a case study using a transitive inference task where essentially people are taught, fictitious facts about presidents and famous people. So, for example, they might have learned that Kennedy is better at chess than Einstein and Roosevelt is worse at chess than Einstein. And then they're probed to answer a question like, true or false, Kennedy is better at chess than Roosevelt. Okay, so given those facts, you might infer that Kennedy is probably better at chess than Roosevelt because Kennedy is better than Einstein and Roosevelt is worse than Einstein. So that's what people would do. What Jerome did in his experiment was that there were actually 5 people altogether, 3 presidents and 2 famous people, Einstein and Presley. All the participants in the study knew who all these people were. And they studied these true or false questions, and they had to learn to answer true or false to them so he could test both humans and language models on this. And there were several different conditions. So there was an aligned condition where Einstein was like one of the best chess players and Presley was one of the worst, but they were still ordered like this. One of the presidents was the best. The presidents were randomly permuted for different subjects, but there's an aligned condition like this and then an unaligned condition where Presley's better than Einstein, but they're never explicitly exposed to that during learning, right? They're only exposed to neighboring pairs during learning. And so we can ask all these inference questions. Okay, so here are the data. In red are the human subjects' data, and you could see that just to learn how to answer these questions, human subjects required 20 passes through the data. Now, I won't say that every subject needed 20 passes through the data. Some of it learned it more quickly than others, but on average, this is the average over a group of human subjects. They got better and better at answering these questions correctly over 20 passes through the set of facts. So people's ability to memorize facts is actually rather slow. And in comparison, if you present the information in context to a language model, it actually performs almost perfectly from one from just one, it's not so good. With 2, it's pretty good. So it's got the information in there twice. It actually helps it. Third time doesn't add much, but it's up its ceiling by then. Okay, so actually it's a little bit more human-like than I remembered there, but still way better, right? I mean, very good use of information in context in terms of learning the explicit facts. That is to say, you've given it all that information and probe it for the stuff that's in its context window. 2 copies of it in its context window is good enough for it to answer those same questions. There's no generalization yet. If you fine-tune it into the weights, it learns very slowly. That's the LoRa curve here, low-rank fine-tuning of the language model. And but let's look at what happens in the inference problems. So for the reverse problems are just the reverse of the problem that was true in the given information. If you taught Kennedy is better than Einstein and you probe with Einstein is worse than Kennedy, that would be true, right? But that's the reverse of it. And humans, are less than perfect on both the learned and the reversed, whereas all the models that were fine-tuned or given this information explicitly are right at ceiling there. But the fine-tuned model is completely a chance with the reverse. The in-context model isn't so good with the reverse unless you let it do a chain of thought, really a rollout. Then it's up at the same level as the humans. Okay, so far so good. But the key point is there's actually 2 kinds of humans. And they're kind of like the two kinds of humans in this Sudoku experiment. One kind of human organized this information in their mind so that if you asked them, could you give me the ranked sequence of who's best to worst, they could do that for you right off the top of their head. And most of them said that they had already worked that out during the learning phase. Or a few said they worked it out at the beginning of the testing phase. But we asked them all these questions about that. And if you give the language model the ranked sequence in context, it can use it to behave just like they did, essentially. I'm not going to walk you through all the details, but that's true. But it doesn't do that itself, right? It doesn't organize its thought processes itself. So that's sort of my message here. These models are, in some ways, sort of like us, but they're not, active, constructive, self-directed thinkers the way Newton and Darwin and Einstein were, So here are my takeaways. When you train neural network models by fine-tuning their connection weights, they learn slowly and generalize very narrowly. In-context learning may be a small step forward, but it is far from a perfect solution. Humans can sometimes learn very quickly from instructions and explanations, forming useful abstractions and organizations of content that support generalization. And my conjecture is that successful human learners are goal-directed learners who seek ways to structure their own understanding. They can make mistakes and go down blind alleys, but with persistence and self-criticism, they can achieve breakthroughs of the kind we associate with the greatest thinkers that we know. And capturing these human abilities is a challenge AI has yet to address. Thank you.
Time for questions. If anyone would like to put your hands up, the volunteers will run the microphones. Any questions for Jay? Yeah, John.
Thanks for the talk. Can you speculate on ways to get towards this? For example, do you think a learner should ask themselves what problems they might face in order to help structure their knowledge?
That's a great question. And I think that is probably part of what we do. We can, when we experience, the smart seminar student is always thinking, well, if that's true, then isn't this also true? And what should I think about that, right? And we are elaborators, and we're thinking ahead about what the implications of ideas are. And in fact, if you let the model take the sentence in context and generate its own elaborations of it, and then train it with what it produces, that actually allows the model to learn in a way that makes it so much actually better. So I ended up being a co-author on a paper about that very subject as part of a team I'm associated with it at DeepMind. Yeah. So thank you for that question.
So Volker first,
and then great talk. Yeah. Okay. Great talk. I think one idea is, and maybe the brain is modular. Should the LLM simply learn to query databases and to query logical things and mathematics, or should it be like internal to the LLM?
Well, that's a great question. You said something about you thought that some people thought the brain was modular? Yeah. So first of all, can I comment on that from my perspective? The brain does have quite diverse parts, and some of them are very, very different from others. Like the hippocampus, for example, is very, very different from the neocortex of the brain. In humans, the hippocampus is only a very, very small part of our brains, but it's the part of our brains that's absolutely crucial for our ability to learn new things quickly. So if the subjects in our experiment had been amnesics, they would never have learned the facts, right? So they're using their hippocampus as the place where they're storing this factual information as they're experiencing it. There's enough different facts and they're presented in enough different ways that you can't just hold on to it explicitly in the very limited sort of working memory that we have. So that's a very important module. I think that these modules are always interactively collaborating with each other, but I think it's reasonable to view without the hippocampus, things that we know well, we don't need it for anymore. So there's a sense in which, when we learn new things, we're learning them in this sort of hippocampal-dependent way, and then we're gradually integrating them into the fabric of our experience in such a way as to, you just know that your uncle's son is, whatever his name is. You don't have to look it up in your hippocampus anymore because you've rehearsed that many, many times. Same thing is true of basic number facts and all kinds of things like that, to the extent that people think that their understanding of basic number must be, God made the natural numbers. All else is the work of man. They remember they had to struggle a little bit to learn, calculus and stuff, but the natural numbers just seem so natural. It's complicated about these modules. I certainly think that there are different modes of thinking that we can engage in. And, when I start thinking as a computer programmer or, how am I going to mathematize this argument or something like that, I'm using what might be the same cognitive system, but in different ways. And I think the hippocampus, is relevant for storing information of many, many different kinds, although the left hippocampus is more related to language-related things and the right more towards, so it's graded in that respect. So I don't know if I'm answering your question, but those are my answers.
Thank you for a great talk. I have a language of thought question. So you pointed out that some of these neural networks, when they're a chain of thought, they perform more human-like, especially they're more like successful human learners that form useful during the thinking process. So I wonder, and when models are a tool of chain of thought, they produce intermediate language output to help them to form their solution. I wonder if you think these successful human learner also use some intermediate abstraction that relies on language, or do you think it's something more distributional? And if it's more distributional, could machine be using something like that as well for intermediate thinking?
I didn't catch every single word, so I'll do my best to answer your question. But so chain of thought is, of course, very widely used anymore in deep learning, right? And the DeepSeek model, that base model I mentioned earlier, that was the base training just doing next token prediction. They did all this subsequent fine-tuning, and they encouraged it to do all these incredibly extensive rollouts of chains of thought using reinforcement learning. And those things do help. The question, many people are asking this question right now, and I'm very doubtful that they're really doing much in the way of structured thinking. They generate extremely long chains of thought, and if you look at what's going on inside some of these chains, it's kind of like garbage and repeating themselves over and over again and stuff. And so again, I'm not an expert in the details of that, but my thought is that generally speaking, when a human who knows something about a domain is solving a problem, they're engaged in a more structured process than that. And this is something that I think is extremely relevant to the success of AI systems like in games like chess or Go or many other AI applications. They exploit the ability to do massive rollouts of various possibilities, and nobody's apologizing for doing that. It's just a way of getting information that no human being would be able to do because you can't keep track of all of that stuff, but you can keep track of it on a computer. So artificial general intelligence is the process of doing massive rollouts and checking on the various answers and using them in various ways. There's a paper called Alpha Geometry, which beat the won a silver medal, not the gold medal in the mathematics Olympiad a couple years ago, but it was doing massive rollouts, and even the authors admitted that probably the human solvers were doing something more conceptual and structured than that. It's not that we don't do certain level of rollout, but we don't, it's more structured and more. So, I'm kind of trying to give you the sense that it's early days in this, right? We shouldn't think that today's models are the final word on anything. Like I said before, probably some architectural breakthroughs will be very useful. And rollouts are important. They are important for human problem solving. I think we do it in more structured ways. I think that's the basic answer to your question. Yeah.
Great question. Thank you, Jay. That's all the time we've got for questions at the moment. But Jay's around all day, and you'll also be on the panel later today at 20 to 4. So let's all give him a round of applause again. Thank you very much.
Thank you.